Thank you very much. My name is Saitoh, and I'm from the University of Tokyo and Tokyo University. So since last week, I work for University of Tokyo and Tokyo University, two universities. Oh, I like the both. I love the both two universities, but my official affiliation is now the University of Tokyo, and I work for the JST and a lot of project too. Okay, so today I'd like to give an introduction to the spin current physics and the spin tunnel physics based on the EEC, atomic garnet. First, I'd like to mention the basic idea of the spin current and how to measure the spin current. And next, I'd like to mention the spin pumping. It is a very nice way to make the spin current in condensed matter. So first, I'd like to show the electron spin pumping, and then I'd like to show the nuclear spin pumping and the spin Seebeck effect, and the spin parity effect, the reverse effect, the spin Seebeck effect. And finally, I'd like to show the spin current probe for material science. So I'd like to measure the rollover spin current in the spin phonon hybridized state, and the spin current in antiferromagnetic material. And if time permits, I'd like to mention the spin current in one-dimensional spin quantum linked state. Okay, first, so what is spin current? Spin current is a flow of spin angular momentum in condensed matter. There are some kinds of spin current in condensed matter. The first one is a very famous one, free electron spin current. Free electron spin current is like this. So if there is a counter propagation of upspin and downspin of free electrons like this, there is no net charge flow, but flow of spin angular momentum is finite. So this is the spin. This is the free electron spin current. So free electron spin current can be written as J up minus J down. So there is no net charge current, but when this value is finite, the spin angular momentum flow is finite. Okay, in fact, the free electron spin current is a very short range in condensed matter. Due to the spin flip scattering or spin orbit scattering, spin loses its memory within a very short length scale. Typically, it is within the 1 micrometer scale. This length scale is called a spin diffusion length. So spin current creation and utilization should be done within this length scale. Next spin current is called a spin wave spin current. Spin wave is, of course, wavy motion of the magnetization in a magnet. When the spin wave population at k is not same as that at minus k, spin wave can carry angular momentum. This is spin wave spin current. So the spin wave spin current can be written as the sum of fk minus f minus k. In fact, spin wave spin current can be seen in terms of heat. So first, I'd like to show it to get familiar with the idea of the spin wave spin current in condensed matter. The idea is very simple. When a spin wave spin current is created in condensed matter, it should carry heat. So the local heating can be achieved. So which can be observed. So this is a very simple idea. How to create spin wave spin current in magnet like EEC. We have used methods using surface spin wave. In the ferromagnet, there is a surface spin wave called a Damon-Eschbach mode. Damon-Eschbach mode is a surface spin wave mode mediated by the magnetostatic coupling, which runs only in this direction, the surface, and only in this direction at this near the bottom surface. It's a kind of a one-way street of the spin wave spin current. But here, this spin current are cancelled out. So we put a sample on the microwave antenna. Then the bottom of the sample is very strongly excited, but the surface is just weakly excited, which gets an imbalance between here, and the finite net spin current appears in this direction. So finite spin current is created by just putting the sample on the microwave antenna. Okay, this work is done by Bucat's group. Okay, so this is a microwave absorption spectrum for EEC. This is the EEC. EEC is put on the microwave antenna. This chart P corresponds to the uniform magnetization cyclic motion called ferromagnetic resonance. This broadband corresponds to the surface spin wave. So when the frequency is within this band, the spin wave spin current is created in this direction. So let's see what happens. Okay, so this is the surface temperature movie measured with some camera. This is the waveguide here, and this is the EEC sample. This movie is measured with sweeping the frequency of microwave. This is the frequency, and we're getting into the ferromagnetic resonance band. So the sample is uniformly heated like this. So just a simple heating. And we are getting out of the ferromagnetic resonance band, so sample is cooled down again. Okay? So this broadband corresponds to the surface spin wave band. So when the frequency is within this band, spin wave spin current is created in this direction. Spin current is created in this direction. So let's see what happens. Okay, now we are getting into the surface spin wave band. So the spin current is gradually created in this direction, and as a result, temperature gradient is spontaneously formed like this. Please note that EEC has a very big band gap, 2.6 eV. So there are no free electrons. So this local heating is due to their spin wave spin current. There are no free electrons. Okay, of course, by reversing the magnetic field, the sign of the temperature gradient is reversed like this. So this is due to the spin wave spin current. Okay, so this is spin wave spin current. And how do we measure free electron spin current? Okay, we have found that a spin current creates an electric field like this. This is the spin current flowing in this direction. And from this spin current, electric field or electric voltage is created in this direction. I'd like to show it by using a simple toy model. The existence of a spin current means that there is a counterpropagation of up and down spins. Since the vector product of spin and velocity of these particles are the same, spin-orbit interaction scatters these two particles in the same direction. As a result, charge current or electromotive force is created in this direction. So electric voltage should appear between here and here. So spin current is converted into the electric voltage via the spin-orbit interaction in condensed matter. So this is a method to measure a spin current. We name this inverse spin Hall effect. This is because this is a reverse process of the famous spin Hall effect. Spin Hall effect is the conversion of charge current into a spin current in which a spin-orbit interaction scatters up spin and down spin into these two directions. A situation in which a spin current is created in this direction. So charge current is converted into spin current via the spin-orbit interaction. This is a reverse process of the spin Hall effect. So we name this effect the inverse spin Hall effect. Okay. So this is how we measure the spin current. Then how do we create a spin current? We have shown that a spin current can be created from some kinds of rotations. So spin current can be created from magnetization rotation. In the Faraday's electromagnetic inductions, charge current is created in the longitudinal motion of the magnetization. But in the spin sector, spin current is created from rotation of magnetization. This is called spin pumping. We also found that a spin current is created from mechanical rotation, but I'd like to skip this because it has nothing to do with the EEC. So I'd like to focus on the spin pumping here. The spin pumping is a creation of spin current from the rotation of magnetization. The mechanism of the spin pumping is like this. This is the it's kind of a simple explanation for the mechanism of the spin pumping. Okay, consider ferromagnet and conductor, and coupling between the magnetization and free electron at here can be written in terms of this spin exchange Hamiltonian, m dot sigma. M is magnetization, which is in a cyclic motion with frequency omega. So it's a rotating magnetization. And the sigma is free electron spin at here, and the free electron spin can be written as parity matrices like this. So spin exchange m dot sigma at here. By using parity matrices, this spin exchange can be written in terms of this matrix form. This matrix element represents the scattering of upspin into upspin. The matrix element is, of course, real fixed number, so basically nothing happens. On the other hand, this matrix element represents the scattering of upspin into downspin. There is a frequency shift factor, which means that scattered down electron is accelerated. On the other hand, this matrix element represents the scattering upspin, scattering of downspin into upspin. There's a negative frequency factor, which means that the scattered upspin is slowed down. As a result, upspin is slowed down, and the downspin is accelerated, but there is no net flow charge. No net flow charge. So there should be a counter propagation of up and downspin like this. So this is a spin current. So from magnetization motion, spin current is created. So from magnetization motion, this is magnet, and we attach a conductor to the magnet. From the magnetization rotation in the magnet, spin current is created. This is the spin pumping. This is a simple setup for the measurement of the spin pumping. This is a kind of platform setup. This sample is very simple bilayer system of EEC and platinum. Okay, so EEC has a very big band gap, so there is no contamination of the charge current in this magnetic layer. Okay, anyway, so we apply the magnetic field to the sample to excite a magnetization rotation. And from this magnetization rotation, a pure spin current is injected into the conductor. And inside the conductor, spin current is converted into the electric body force via the spin Hall effect. So the voltage appears between here and here. Okay, so this is the spin current creation and measurement. This is a very fundamental setup, and this is a result, and this is a voltage that functions the magnetic field. At the ferromagnetic resonance condition, voltage appears, and by sweeping the angle of the magnetization, the amplitude of the voltage exhibits a sinusoidal variation, which is consistent with the symmetry of the inverse spin Hall effect. So this voltage is due to the is attributed to the inverse spin Hall effect induced by the spin pumping. Spin pumping is a universal method for spin current injection. So you can inject spin current into any material. They say the spin current injection in organic semiconductor P.PSS. So you can see peaks here and here. And this is the spin current injection in the surface state of topological insulators, BSDS. So you can see peaks here and here. This is a correlation with Anderson. He is now moved to the Cologne University. Okay, so this is the coherent spin pumping from electron magnetization. Then I'd like to move on to the nuclear sector. I'd like to show the nuclear spin wave spin pumping. Nuclear spin wave is a kind of a hybridized mode between the magnetization motion and nuclear spin dynamics. It is mediated by the famous Saitoh-Nakamura interaction. It is made of the hyperfine coupling which connects the nuclear spin and magnetization, and spin exchange coupling between the magnetization. So via Saitoh-Nakamura coupling, the the hybridized state of the nuclear spin and magnetization is made. And the nuclear branch of this hybridized state is called the nuclear spin wave. And via this hybridization, strong coupling between the nuclear spin and magnetization is made, which may realize in nuclear magnetic resonance induced spin pumping, NMR spin pumping, when we put a conductor layer on the top of this material. Okay, so then what is the required condition for the nuclear spin wave spin pumping? Basically, we need a single crystal which exhibit large nuclear spin, and natural abundance of this magnetic isotope is almost 100%. And magnetic order is necessary because to keep coherence and to allow the coupling between the magnetization and nuclear spin. Weak magnetic anisotropy or small spin gap is necessary. So orbital angular momentum should be 0. And the final magnetization is necessary for the final spin pumping. And of course, the sound-Nakamura interaction should be strong. So this is the condition. So we looked for material which satisfy these conditions, and we found nuclear spin pumping in the antiferromagnetic material in which the nuclear spin wave has been well established long years ago. That is manganese carbonate, manganese CO3. In this material, nuclear spin wave due to the Saitoh-Nakamura coupling has well been established long years ago. And in this material, divalent manganese is a good ion, because manganese divalent ion has a very large nuclear spin, 5/2, and it is 100% of natural abundance. And it exhibits undifferent order and exhibits a weak ferromagnetism due to the DM interaction in the undifferent phase. So the magnetization can be finite, which is necessary for the efficient spin pumping. And luckily, the orbital angular momentum is almost 0. So the spin wave gap is very small, which allows the hybridization between the nuclear spin and spin waves in this material. Okay, so we put a platinum layer on the top of this material and measure the spin waves, nuclear spin wave spin pumping. So this is the magnetization as a function of the temperature. And nail temperature is 35 Kelvin. So below this temperature, the weak ferromagnetic component appears like this. This is due to the strong DM coupling in this material. And in this material, the nuclear spin wave is very established, and this is calculated the nuclear spin wave as a function of the magnetic field. Okay, first we measured nuclear magnetic resonance for this material. And this is NMR spectrum as a function of the frequency. You can see peaks here and here. And by changing the magnetic field, the frequency of the nuclear magnetic resonance is shifted like this, but it is far from linear dependence. And this nonlinearity is called the frequency pulling effect. It is due to the hyperfine coupling. In fact, the magnetic field dependence of the nuclear magnetic resonance frequency is very consistent with a calculation for the frequency pulling effect in which nuclear spin formation is taken into consideration. And the estimated effective field for the hyperfine coupling is strongly enhanced around 3 Kelvin, which means that nuclear spin wave is formed around 3 Kelvin. Then we put a platinum layer on the top and measure the spin pumping with applying the radio frequency wave to this material. This is voltage as a function of the frequency. At 3 Kelvin, there is no signal, but lowering the system temperature, voltage peak appears like this at the nuclear magnetic resonance frequency. Okay. This is the temperature dependence of the intensity of the voltage, like this. the voltage suddenly appears around 3 Kelvin. And this temperature dependence has nothing to do with the temperature dependence of the radio frequency wave absorption, but it rather coincides with the appearance of the frequency pulling effect. So this data says that voltage appears concomitant with the formation of the nuclear spin wave. Okay. So this is the magnetic field dependence. By reversing the magnetic field, the sign of the voltage is reversed like this. So which shows that this voltage peak is due to the spin current. In fact, this voltage peak is consistent with the nuclear spin wave spin pumping, and because the temperature dependence of this peak is consistent with the calculation for the nuclear spin pumping. We calculated spin pumping by solving the LLG formula for the magnetization and the Bloch formula for the nuclear spin. And this is the calculated result as a function of the field. This is the inverse spin Hall effect voltage, a function of the field. Which is very consistent with what we observed in this material. Okay, so we attributed this to the nuclear spin wave spin pumping. Okay, anyway, so this is spin pumping. So we showed that the spin current can be created for the rotation of magnetization. Then spin pumping and inverse spin Hall effect are two important features in the spin current in the spin current physics. So the spin current is created from rotation, the magnetization, and which can be observed in terms of the electromotive force. Okay, then next I'd like to show that not only coherent mode, thermal fluctuation can realize spin pumping, which is called a spin civic effect. Spin pumping can be caused even by thermal fluctuation. First, let's consider spin dynamics. Basically, angular momentum of electron is basically along its magnetization. And as a result, the magnetization inertial motion in a magnet is anticlockwise only. There is no inertial clockwise motion. Inertial motion in a magnet is anticlockwise only. This requirement is very strong. This feature is called a non-reciprocity. It is due to the kind of the lowered symmetry in the time reversal. And this requirement is very strong that it is unchanged even when thermal fluctuation create magnetization motion. Thermal magnetization fluctuation looks very random, but it can rotate anticlockwise only on average. So when a part of the sample is heated, thermal fluctuation induces unidirectional magnetization on average. And please remember two important features for spin current. Spin pumping converts unidirectional rotation of the magnetization into a spin current, and the spin current is converted into the charge voltage. So when thermal fluctuation spontaneously create unidirectional rotation of magnetization, then spin pumping converts this magnetization rotation into a spin current. Then the spin current is converted into the electric motive force via the spin Hall effect. So when the sample is heated, spin current is spontaneously created. This is called a spin civic effect. And the resultant spin current is proportional to the spin wave population function minus electron spin fluctuation function. When this value is finite, spin current is created. This is spin civic effect. It's a summary spin pumping. The setup is also very simple. This is also the same configuration equation barrier system. So when a part of the sample is heated, thermal magnetization motion injects a spin current via spin pumping, And this injected spin current is converted into the electromotive force by the spin Hall effect. So voltage appears here and here. This is data. By applying the temperature gradient, voltage appears like this, and by reversing the temperature gradient direction, the sign of voltage is reversed like this. Okay, this is the spin Seebeck effect. This is magnetic field dependence. By reversing the magnetic field, the sign of voltage is reversed like this. And what if we applied much stronger magnetic field? We found that the spin Seebeck effect is completely suppressed like this at low temperature. By applying 40 Tesla, the spin Seebeck effect is completely suppressed in spite of the saturation of magnetization. So this shows again that the spin Seebeck effect is due to the thermal fluctuation of magnetization. By applying very strong magnetic field, thermal fluctuation of the magnetization is completely suppressed by opening the gap in the spin wave as spin wave spectrum like this. Okay, so this data shows that the spin Seebeck effect is due to the thermal fluctuation of the magnetization. So the thermal fluctuation is very fragile under a strong magnetic field. Okay, the spin Seebeck effect is very simple structure, just a magnet, just a simple film. So some Japanese companies are making some electric converter based on the spin Seebeck effect. This is the evolution of the efficiency of the spin Seebeck effect. When we found the spin Seebeck effect about 7 years ago, the efficiency was very, very bad, but it has gotten better, about 400 times greater in terms of the ZT factor. Now the spin Seebeck effect is as good as the N-type as silicon. Okay, so this is spin Seebeck effect. Next, I'd like to kind of the reverse effect. It is called a spin parity effect. Spin parity effect is a reverse effect of the spin Seebeck effect. So when we apply the spin current injected into the magnet, this is the conductor, this is EEC, and when charge current is applied in this direction, spin current is created, and spin current is put into the magnetic layer. Then, as a reverse process of the spin Seebeck effect, heat current should be created. So a part of the sample is heated or cooled, depending on the direction of the spin current direction. So one can cool or heat the surface of this system by changing the polarity of the spin current. The first measurement of the spin parity effect was done by the Bart Banfi's group in Netherlands, not our group. This data is Bart Banfi's group data. So he put a platinum wire on the top of EEC, like this. This is EEC, and he put a platinum layer on the top. This is a platinum layer, and he applied a DC current here. And he put a fine, very small sum couples. This sum couple is used for the temperature measurement. Okay, and they observe the surface temperature of EEC is changed like this by changing the magnetic field, which is consistent with the prediction of the spin parity effect. Okay, so this is the first observation of spin parity effect. So we thought of some moving method for the spin parity effect. The setup is like this. We put this type of the conductor wire, and this is EEC. The magnetization is in this direction. So a current is applied in this direction. Then in this part, the spin current is injected in this direction from EEC to conductor. So the result, heat current is along this in this direction. So the surface of this metal layer should be heated. On the other hand, in this part, the spin charge current is in this direction, so the spin current direction is here, and the heat current direction is in this direction. So this part is basically cooled down. And in this part, nothing happens because the spin acceleration is perpendicular to the magnetization. So basically nothing happens. So we observe this subtle temperature change with using the thermal camera, which I showed you. So we apply the AC charge current to the sample, and we measure the sample surface temperature image by using the thermal camera. But by using the lock-in method, we can measure the temperature change very precisely. Okay, so this is the result. This is the, this part is heated and this part is cooled down. And by applying the amplitude of the current, there's a gradual change of this heating and cooling part. The temperature change is just a 20 maybe the amplitude is a millikelvin. So this the very small change of temperature can be measured by using this method. Okay, the mechanism of spin parity effect is like this. When this kind of spin acceleration is forward in the conductor layer, the predominant scattering is like this, from upspin to downspin. Because of the angular momentum conservation, this means the Magnum number should be enhanced. And this frequency change is handed to the Magnum frequency change. So this means the Magnum sector is heated and the metal sector should be cooled down. On the other hand, when this kind of spin acceleration is formed here, predominant scattering is from here to here. So the downspin is scattered into upspin. As a result of the angular momentum conservation between free electron and magnetization, Magnum number should be suppressed because the Magnum has spin 1. Okay, so as a result of the spin angular momentum conservation, Magnum number is reduced, and the frequency change is handed to the Magnum frequency. So in this case, the insulator part is cooled and the metal part is heated. So as a result of angular momentum conservation and frequency conservation, we can control the heat current by using the spin current. Okay, so this is the spin parity effect. Finally, I'd like to show the how to detect material property by using spin current. First, I'd like to show the Phonon-spin hybridization in the EEC. First, take a look at this. Okay, first take a look at this data. This is a spin civic effect in EEC, magnetic field and voltage here. You can see small peaks here and here. I thought these were just a noise, but we found this data is very reproducible. Then one of our good students, Mr. Kikawa-san, now he's assistant professor in my group. So he noticed that this peak field coincides with a point touching condition between the phonon and the spin wave mode. This is a phonon, this is a spin wave dispersion relation, wave vector and frequency, spin wave and phonon. And with the prime magnetic fields, the spin wave dispersion is shifted to a higher frequency, but phonon does not move. So the number of intersection between phonon and spin wave changes from 2 to 1, and at last there is no intersections. This condition is called a point touching condition, and by using material parameter of EEC, spin wave stiffness, stiffness, and the phonon sound velocity, we calculated the point touching condition should appear at 2.6 Tesla, which coincide with this peak position. Okay, so we suggest that the phonon spin wave intersection might change the spin civic effect. At near this intersection point, phonon spin wave hybridized state should be formed like this. And how does spin wave phonon hybridization affect the spin civic effect? So we started collaboration with Gerrit Bauer and the Lembad because they already started the calculation of the Magnum Phonon formation. And what is important here is that there are two phonons, LA phonon and TA phonons. LA phonon is a longitudinal mode like this, and the TA phonon is a transverse mode, LA and TA phonon. And if this intersection is what we found, there should be another point touching condition, point touching to the LA phonon. Okay, so by using material parameters again, we calculated that the another point touching condition should appear at 9.3 Tesla. It's a point touching to the LA phonon. So we went in hand for another peak around this field. The result is like this. So this has been specific effect. So we can peak here, we can see peak here, and we went to the higher field range, and we found another peak at 9.3 Tesla, just as the field expected for the another point touching condition with LA phonon. Okay, this is the temperature dependence. With decreasing the temperature, intensive specific effect is gradually suppressed, but peak structure at lower field becomes sharper. It's like this, so it is 50 Kelvin, the peaks are still vague. It's a weak peak, but lowering temperature, 6, and this is 3 Kelvin. At lower temperature, the peak became sharper, and at lower temperature, the peak rather predominate the spin specific effect. Okay, so the 50 Kelvin and 3 Kelvin. At low temperature, the peak is the most significant component, the spin specific effect. So this is a comparison with the theoretical calculation done by the Kashem, Benedetta, and Lambert, and Garrett. And in this calculation, the summer spin flow was calculated based on the Boltzmann framework. And it shows that the spin wave flow is strengthened via hybridization with phonons when the lifetime phonon is greater than the lifetime of spin waves. When this condition is satisfied, spin wave lifetime gets longer via the hybridization with phonon, because the phonon has a much longer lifetime. Okay, so in this via the hybridization, the spin wave lifetime gets longer, and at the point touching condition, this enhancement effect is maximized because of the maximum phase space volume between the phonon and the spin wave hybridization. It is a normal intersection condition. The hybridization volume is like this, but in the point touching condition, hybridized volume is very large. So in this condition, hybridization is rather maximized. Furthermore, at a point touching condition, the group velocity of phonon and the spin wave coincide. So, which means that hybridization should be strengthened in this point touching condition. So, this is the reason for the peak to appear in the spin specific effect. So, what about other sample? This is bulk intermal garnet. You can see peaks here and here. But maybe the peaks are too weak. But by looking over the data again, this is a magnified view. You can see small peaks here and here. So peaks are very, very small, but kind of a universal feature. So this is lower temperature. There's also small peaks here and here. So this phenomenon may be very universal feature in the spin specific effect. The phonon anomaly in the spin specific effect can be used as kind of spectroscopy for the phonon spin wave coupling. Okay, in fact, the Phonon-spin hybridized state manifests also itself in some other spectroscopic measurements, like the famous Brilliant light scattering and the neutron scattering and ultra-fast time resolved optical spectroscopy. Among them, today I'd like to show some of the data from the ultra-fast time resolved optical spectroscopy for my group. So the measurement is very, very simple. We use two light pulse. The first pump pulse is used to create spin wave. The pump pulse is injected at the center of the sample, and from this spot, a bunch of the spin wave is created. And this should propagate in the sample, and this propagation is measured by using the second light probe, light pulse called the probe pulse. And by using the Fourier transformation, we can get the spectra of the spin wave. So this work is done by the Saitoh group and the Nakamura group, and we received advice from the VUCAD. And this is what we observed. Basically, so light is injected at the center of the sample. This is not simulation. This is what we measured in this sample. And light is injected at the center of the sample. The various pattern is observed. This is the time-resolved spectroscopy. But note that this is not the wavefront of the spin wave. This is the interference pattern of many spin waves. Okay, so by performing the Fourier transformation for this data, we obtain this spectrum, the band structure of spin wave. This is the spectral intensity function of the wave vector and frequency. You can see a signal here and here. This corresponds to the surface mode of the magnetic wave, and this corresponds to the volume spin wave. Okay, this is the angular dependence. So we can rotate sample numerically. So this is the cross-section, wave vector, and frequency. And we can see the magnetic wave here, and this is phonon. This is the manifold of the spin waves. And this is a time-resolved spectrum. This is done by the wave rate analysis for the data. So the spectral weight is accumulated at this point. Okay. So this is angular dependence. This is angular dependence. So you can see spin waves here, 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 here. This is basically Damon H-bar mode and the volume mode, and these are phonons. The Damon H-bar mode is consistent with the calculation of the magnetic Umov calculation. Okay, so these are spin waves. And this is the temporal evolution data, time-resolved data, 2 nanoseconds to 10 nanoseconds. This point corresponds to the phonon-magnon intersection point, which I showed you. So this data shows that the spectral weight is accumulated at this point. This is due to the formation of the phonon spin wave hybridized state. Okay. So Phonon-spin hybridized state is very significant in the spin transport in EEG. Okay, finally, I'd like to show some data in the antiferromagnet. So, in fact, the spin pumping can be used for measuring the magnetic property in very thin films because spin pumping is related to the magnetization just as a boundary to the conductor. So it means that it is very sensitive to the magnetic susceptibility here. So spin pumping may measure the susceptibility of a very thin film by putting the thin film at the junction in a spin pumping system like this. So consider the EEG and metal, the very standard spin pumping system. When insert the very thin film at the junction, we can measure the magnetic property of this material. So the first example is the cobalt oxide. Cobalt oxide is known to exhibit undifferent order. And we made a third layer sample the platinum cobalt O and EEG. This is a very thin layer. And we measure the spin current creation and the spin current measurement in this metallic layer. Okay? This is the data without the cobalt oxide layer. So this is a simple bilayer system. The temperature dependency is very simple. This corresponds to a change in the resistivity of this fraction layer. Then we put cobalt O. Then a peak appears here, and this peak corresponds to the narrow temperature of the cobalt oxide. So this data shows that spin current signal is reinforced at a narrow temperature. In fact, by changing the narrow temperature, we're changing the thickness of this film. The peak position is shifted in response to the change in the narrow temperature of this material. So this data shows that spin current is spin conductivity is reinforced, reflecting the enhancement of the spin susceptibility near the near temperature. Enhanced spin susceptibility means that magnetization deformation is basically softened, which means that the spin current is more put in this material. So spin current in efficiency is better near the narrow temperature. Okay, this work was done by Yarosov, but there is another issue, because in this antiformed order, there are many marginal structure, because the cobalt O is not so anisotropic, so the Néel vector is randomly put. Okay, so the Néel vector is very random, and which makes the spin transport in this antiformed phase very complicated. So isn't it possible to make a sample in which the Néel vector is uniformly oriented? Yes, it is possible. We can make the chromium oxide, chromium 203. It has a corundum structure, and anisotropy is along the c-axis. And luckily, in this material, c-axis is completely aligned along the normal direction on the EEC due to the epitaxial condition. So this matching is very good between the AB lattice and EEC. So the c-axis is completely aligned in the normal direction. So the anisotropy direction, magnetic anisotropy, is aligned in this direction. So the Néel vector is aligned in this direction. So in this configuration, we can expect that the Néel vector is very aligned in the c-axis in the normal direction. So we measure the spin civic effect in this material. Okay, so as usual, this is just spin-civic effect without any magnetic layer. And in this material, we have a sudden change of the spin current signal at a near temperature, very steep. And this steep change appears also when the copper layer is put between the two, EEC, copper, chromium oxide, and platinum sample. In this configuration, maybe the orientation is not 100%, so the structure is vague, but still some change is observed here. In the EEC chromium oxide platinum two-layer system, we observed a very sharp change. This is angular dependence. This is angular dependence of the spin current signal. So this angular dependence is consistent with a calculation based on the model in which we assume the only magnon whose spin is along the Néel vector can carry spin current efficiently. Magnon whose spin is perpendicular to the Néel vector quickly relax because of the strong anisotropy field. So this spin component is quickly decayed, but this spin component along the Néel vector can survive for the longer length scale. We assume such a property, and this result is consistent with the angular dependence. So in this antiferrant phase, c-axis is completely aligned along the normal direction. So this spin wave spin current is completely decayed in the antiferrant layer. So there's a steep change in the spin current. So this should be kind of an intrinsic feature on the antiferrant material. So I think it's a final. I'd like to show the kind of the another type of the spin current by the spinon. So we have shown the free electron spin current and spin current, and there is another type of spin current carriers, which is the spinons. Spinon is excitation from the quantum spin liquid state. A certain type of spinon is excitation from the quantum liquid with single correlation. which can be written in terms of the fermion particle. Okay, so let's compare the spin wave spin current and spin-on-spin current. So for the measurement of the spin civic effect, first we have to apply magnetic field to align the magnetization. Then we apply heat to put fluctuation to the system. Okay, in the ferromagnetic case, the ground state is fully spin polarized ferromagnetic state. So magnetization is fully spin polarized. So when fluctuation is put into the sample, this fluctuation should reduce this magnetization. So fluctuation has negative spin polarization, which is carried by spin waves. So which means that a spin wave has negative spin polarization. So the temperature dependence of the magnetization has negative slope like this. On the other hand, in the spin-on case, a certain type of spin-on is a fluctuation from the singlet correlated state. So when fluctuation is put into the state, this fluctuation should suppress this singlet correlation. As a result, finite magnetization along the magnetic field should appear. So what fluctuation has is positive spin polarization. This positive spin polarization is carried by spin-ons. Okay? So the spin-on has positive spin polarization, and temperature dependence of the magnetization has a positive slope. Okay, so but however, many of the spin liquid in the real world has a very short correlation lengths of spin, so it is not suitable for spin-torus application. But however, there is among them a good sample, a good system. That is a Luttinger quantum spin liquid in one-dimensional spin chain. Luttinger spin liquid may exhibit a long-range spin correlation due to the critical quantum spin fluctuation. It is realized in the one-dimensional spin chain, spin half chain with indifferent coupling. Okay, so the excitation from the Luttinger state is also a spin-on. Basically, this is the paramagnetic state. In spite of the long-range static ordering, collective excitation, soliton type collective excitation may appear. This is the spin-on. So the spin-on is a spin half fractional excitation, and the spin-on spectrum of the spin-on is like this. This is a spin excitation spectrum, Q vector, and this is frequency. This is called a spin-on band. This band is confined by the neutron scattering, and this is susceptibility, the function of temperature for the spin-on system, and it has a positive slope here, so which means that a spin-on has a positive spin polarization. So a good point for the spin-on is there is no gap, because when a spin wave case, by applying the magnetic field, gap appears in the spin wave sector, but in the spin-on case, by applying the magnetic field, this point is shifted along the k vector. There is no gap. Because of the interference of the quantum fluctuation. So there's no gap up to the scale of J, like the 1000 Kelvin. So this gapless feature is very stable. The typical material in feature spin-on is very established, the strontium copper oxide 213. This is a high tissue cupellate related material. In feature spin chain, spin half chain formed along the B axis. This is the spin chain. The copper is aligned in this B along the B chain, and the strontium separate these two spin chains. So it's a kind of shoot one-dimensional spin chain. And the spin-on spectrum is well established by using the neutron scattering, and this is temperature dependence of thermal conductivity, and there is so-called spin-on peak here, so which means that the spin-on transport is predominant in this temperature range. We measured spin-on induced spin civic effect in this material to check the spin current, spin-on spin current in this material. So with the platinum put on the single crystal strontium copper oxide 213, and we applied heat current along the spin chain. Okay. So when the spin-on-spin current is created in this material and when it is put into this metallic layer, this spin current is converted into the electric voltage between here and here via the spin-Hall effect. Okay, this is the data without a spin chain material. So what is observed here is a simple normal length component in this metallic layer. So this is the magnetic field dependence. So this is a sign of the Ness effect. So this data says that the normal Ness effect in this fraction layer is of positive sign. Same sign and the specific effect in the famous fraction layer system. Okay, this is the normal Ness effect in this layer. Then we put a spin chain material. We measure the voltage in the strontium copper oxide 213 and the fraction barrier system. This is data around the room temperature. The voltage is still of positive sign. So this voltage is attributed to the normal Ness effect in this conduction layer. Then we go to the lower temperature range and we found strong negative signal appears at the lower temperature. So which means that the negative, the positive spin current is created in this direction. We confirm that this contribution is due to the spin current because by replacing the platinum layer with tungsten is not exhibit the negative spin Hall angle. The sign of this voltage is reversed like this. And by applying heat current perpendicular to the spin chain, this signal is not observed. So this data shows that the spin current is created along the spin chain, and the sign of spin current is positive, consistent with the prediction of the spin-on-spin Seebeck effect. In fact, it's consistent with the calculation. This is a calculation for the spin-on-spin as Seebeck effect based on the expanded bosonization method and the linear response theory done by Saitoh-san. This is consistent with what we found. Okay, so in this material, nail temperature is about 5 Kelvin. So below this temperature, undifferent phase appears. And this undifferent phase, this negative voltage signal is not observed. So this is consistent with the prediction of spin-on-spin Seebeck effect. Okay, this is the final page. So this is a comparison between the spin wave spin Seebeck effect and the spin-on-spin Seebeck effect. Okay, in the spin wave case, the spin Seebeck effect is strongly suppressed by applying a magnetic field because gap appears in the spin wave sector. So the spin wave is very fragile. Thermal fluctuation is very fragile in the strong magnetic field. On the other hand, gapless future is very protected in the spin liquid system because of quantum fluctuation. In the gapless future of the spinor spectrum is protected up to the scale of J. It's like the 1000 Kelvin. So it's very stable, and there is no suppression of spin Seebeck effect in up to very higher field. So the quantum fluctuation is very stable under the magnetic field. Okay, this is the advantage of the spinon in the context of the spin current physics. Of course, unfortunately, amplitude is very small in the spinon case. Of course, the amplitude is much, much stronger in the spin wave case. Okay, so it is time. So this is summary of my talk. We gave us 3 topics. So how to measure spin current. Inverse spin Hall effect is a very handy way to measure spin current. And how to create spin current in EEC. Spin pumping is a very good method. And the nuclear spin pumping was found. And the spin Seebeck effect is also a very handy method. Just putting a heat to the sample, the spin current, spin wave spin current is measured, which can inject a spin current into the attached metal. And the spin parity effect was also found. It's a reverse process of the spin Seebeck effect. And the spin current can be used to study the material property. So we show the spin phonon hybridization in the spin Seebeck effect. And the spin current is very anisotropic. It's a kind of a nematic anisotropy in the antiferromagnetic material. And we showed the spin-on-spin current in the 1D quantum spin change. Thank you very much for your attention. I'd like to thank you much. I'd like to thank the collaboration between our group, and thank you for the collaboration between the wonderful theoreticians, Gerrit and Kashen and the Micah Sense group, and the Salamich Takai's group, and Lambert and Benedetta, and the Yaroslav and Helen in Mainz, and Brugard group, and the Matthias group, and the Bumfield's group, and Ricard group, and Schaufenjin's group, Schillinghaus in Cambridge, at Kurebashi UCL, and Dr. And who moved to Karen.